Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue discussing the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. And today we discuss the solution of a problem from the section Real Analysis, which is related to the concepts of the functions of several variables. And this question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 704149. This question is suitable for all these examinations. Right. The given question is: consider the function f from r square to r defined by f of x comma y, the ordered pair, is equal to x square y by x to the power of 4 plus y square plus e power xy, when the ordered pair x comma y not equal to 0 comma 0, and it is equal to 1 when x comma y, the ordered pair, is equal to the ordered pair 0 comma 0. Which of the following statements are true? We are given four options. Option 1, f is differentiable on r square minus the singleton set consisting of the ordered pair 0 comma 0. Option 2, all directional derivatives of f exist at 0 comma 0. Option 3, f is differentiable on r square. Option 4, f is not continuous at 0 comma 0. Right. Let's now discuss the solution of the problem in detail. We have the function f from r square to r defined like this. Agreed. Now let's call on option 4. F is not continuous at 0 comma 0. Is it so? So we will now consider the ordered pair x comma y tending to 0 comma 0, the ordered pair, along the path y is equal to mx square. Limit x comma y tends to 0 comma 0 of f of xy along the path y is equal to mx square will become limit x tends to 0 of x square into y is mx square by x to the power of 4 plus y square, that mx square whole square, plus e to the power of x into y mx square. Right. As x tends to 0, this will be m by 1 plus m square, agreed, plus 1. This depends on m and differs from path to path. Limit when exists must be unique. Therefore, f is not continuous at 0 comma 0. The limit when it exists is unique, but it is not here. Therefore, limit x comma y tends to 0 comma 0 of f of x comma y does not exist. Therefore, fxy is not continuous at the origin, that is 0 comma 0. And option 4 is also precisely the same thing given. Therefore, option 4 is true. We continue in the next slide. We have shown already f is not continuous at the origin. Now, we claim f is not differentiable at 0, 0. Assume f is differentiable at 0, 0. This will imply f is continuous at 0, 0. Why? Continuity always implies differentiability. Differentiability always implies continuity. I am sorry. So, f is continuous at 0, 0 you get. But it is not so. F is not continuous at 0, 0. It's a contradiction. Therefore, your assumption that f is differentiable at 0, 0 is not true. Therefore, f is not differentiable at 0, 0. Right? So, our claim is true. Now, we call on option 3, f is differentiable on whole of R square. If f is differentiable on all of R square, means what? F is differentiable at every point of R square. Means what? F is differentiable, but f is not differentiable at 0, 0, which is a point of R square. Therefore, f is not differentiable on R square. Right. Thus, option 3 is not true. In option 3, it is given f is differentiable on R square, but we got it is not differentiable on whole of R square. Right. Option 3 is not true. We continue in the next slide. We have already seen f is not differentiable at 0, 0. Now we call on option 1, f is differentiable on whole of R square except at the origin. Note that the first one, f of xy, is the sum of two functions. The first function you consider, that is x square, this is a quotient, x square y by x to the power of 4 plus y square. It is a quotient of two polynomials, and you know the polynomials are differentiable everywhere, but this is a quotient of two polynomials. This is differentiable everywhere except at the points where the denominator vanishes. It is differentiable everywhere except at the points where the denominator is 0. That is, the denominator x to the power of 4 plus y square is equal to 0 will imply x is equal to 0 and y is equal to 0. That is at 0, 0. At 0, 0. So that means x square y by x to the power of 4 plus y square is differentiable everywhere except at 0, 0. And the next function is e to the power of xy. It is well known the exponential functions is differentiable everywhere. It's a function of two variables, and it is well known e to the power of xy is differentiable everywhere. Therefore, you take the sum, it is sum. Thus, fxy, the sum of these two, is differentiable everywhere except at 0, 0. That's right. That's what precisely option 1 says. Therefore, f is differentiable on R square except at the origin. Thus, option 1 is true. Right. We move to the next option in the next slide. So, option 2, all the directional derivatives of f exist at 0, 0. Let's recall the definition of the directional derivative of f of x, y at a point a, b in the direction of the vector u is equal to u1, u2 is the directional derivative of f at a, b in the direction of u is equal to limit t tends to 0 of f of a plus tu1, b plus tu2 minus f of a, b by t, where u is a unit vector. Agreed. And now the directional derivative of f of x, y at the origin 0, 0 in the direction of u is equal to u1, u2 is In the above, wherever there is a, b, substitute 0. So the directional derivative of f at 0, 0 in the direction of u is limit t tends to 0, f of 0 plus tu1, 0 plus tu2 minus f of 0, 0 by t. And that is limit t tends to 0, f of tu1, tu2 minus f of 0, 0 is 1 by t. Right. So this is our function. So in this, substitute x is equal to tu1, y is equal to tu2, and right. This is limit t tends to 0, we have substituted minus 1 by t. And simplified, limit t tends to 0, t cube u1 square u2 by t square is taken common into t square u1 to the power 4 plus u2 square plus e power t square u1 u2 minus 1 by t. Take this one, the quotient part, take, and the t cancels. And that will be limit t tends to 0, u1 square u2 by t square u1 to the power 4 plus u2 square, t cube cancels, plus limit t tends to 0, e power t square u1 u2 minus 1 by t. Now if you take the limit t tends to 0, it will be u1 square by u2 by u2 square. u1 square u2 by u2 square. u2 cancels and you will get u1 square by u2. But here as t tends to 0, it is 1 minus 1, 0 by as t tends to 0, 0. It takes the 0 by 0 form, which is an indeterminate form. To evaluate this one, we will use LHR, L'Hopital's rule. Right, u1 square by u2 plus limit t tends to 0, the derivative of the numerator, that is 2t u1 u2 e power t square u1 u2 by derivative of t is 1. As t tends to 0, at t tends to 0, it is 0. Thus, you will get u1 square by u2. Thus, this exists when u2 not equal to 0, because u2 is sitting in the denominator. It exists, directional derivative exists. So the directional derivative of f of xy at 0, 0 in the direction of u is equal to u1, u2 exists when u2 not equal to 0. So what happens when u2 is 0? Will the directional derivative exist even in that situation also? Let's discuss that in the next slide. Right. We are continuing the option 2. We have already seen the directional derivative of f of x comma y at 0, 0 in the direction of u, the ordered pair u1, u2 exists when u2 not equal to 0. Let's now suppose u2 is equal to 0. Then the directional derivative of f of u in the direction of u, in that direction u is u1, u2, but u2 you have taken 0, therefore in the direction of u is u1, 0. So this will be limit t tends to 0, f of 0 plus tu1 plus 0, 0 plus tu2, but u2 is 0, therefore it is 0, minus f of 0, 0 by t. Thus you get limit t tends to 0, f of tu1, 0 minus 1 by t. Right. So now look at the function. So for x you substitute tu1, for y you substitute 0. So this will be 0. E to the power of 0 is 1 minus 1. This is f of 0, 0 is 1. So it is 1 minus 1, 0, 0. So limit t tends to 0. This is 0 when u2 is 0. When u2 is 0, it is 0. Right. So thus, combining the above two cases, all the directional derivatives of f exist at 0, 0. Thus, option 2 is true. Summarizing all the options, the answer to this question is options 1, 2 and 4. That is the detailed discussion of the solution of this problem. Whenever you are studying the functions of several variables, you must know how to show that a function of two variables is continuous at a given particular point. Sometimes epsilon deltas will be useful. Sometimes if it is not continuous, use different paths and show the limit different on different paths and conclude it's not continuous. And in this, you prepare a notes. The definition of a function of two variables is differentiable at a given point a comma b. That's a good definition, and you must be sure about that one, and you should know how to show that functions of two variables is differentiable at a comma b. And also finding the directional derivatives. That directional derivatives at a given point in any direction, you should know the definition of that one, and the methods of finding the directional derivatives you must be sure. So go to the functions of several variables and study all the concepts and write down a very systematic notes and work out some problems related to that. I am sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will definitely meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.